And here what we are going to do is look at the sources of contrast, right, that we come up in. So what we have covered so far, we have covered starting with spin, right? We know what is the physics of the signal and how are we trying to convert this spin property or the spin characteristics of the tissue material, whatever we discussed, uh, how is it converted to a voltage signal? That's what we covered so far. So now moving beyond this, we are interested in magnetic resonance imaging. That means we would like to see contrast between different locations, right? And that means we talked about all voxel and we talked about the magnetization vector and how this magnetization vector is the component in the transverse direction is measured, and you get a voltage, a free induction voltage, right? So that is a signal that we got. So now the question is, if I have a distribution of these voxels, right, each one is having its own properties. If I take an image, right, will one location, how will I ensure that one location which has different property, what property we covered, right? We'll rehearse it now. How is it different from another location? That means if you see a contrast from one location to another, in our imaging parlance, if some location is black, the other location is white, right? You see a contrast, black and white. So how does this come? What does this mean, right? How is this related to the signal that we covered so far? That is going to be the coverage in this module. It's going to be very short because I assume you've been through all the video recordings before and you made your effort to read it from textbook multiple times. So you have your own imagination of what is this fundamental signal and how we are going to measure it. So with that background, I think you should be able to really appreciate the how the contrast is generated. So to just before I list it, rest yourself from whatever we covered. Where do you think the contrast come from? So based on this course, you know there is going to be first inherent contrast, the physics based. So what is the inherent contrast we are interested here? Right? Think about it. What is it? Well, you might think of, okay, where is the signal? Okay, I am measuring something that is proportional to proton density. So if I have different proton density, then maybe the different locations will have a different value of bright or dark. Okay, so inherent contrast would arise from proton density, distribution of your proton density. Is that all? Is there any other intrinsic property? Well, we talked about proton density giving you magnetization vector, and then we talked about the signal, the rate at which it is losing the signal, right? So the transverse component is dephasing. So we talked about inherent characteristics, which is T2 or T2 star to be more have that detail as well. So something to do with dephasing, and then we also associated some other material property in terms of time constant with which it comes back to equilibrium. So inherent contrast that we are looking at of each of the tissue property so far what we have covered has to do with difference in proton density, difference in time constant with which it is losing the signal due to dephasing, and time constant with which the location is coming back to the equilibrium or the Z component is building up. These are the three inherent contrasts. Okay, so proton density T1, T2 changes from tissue one location to another location. So is that all? Is there any other thing that we need to worry about before we talk about the contrast? Yes. Remember, this is just the physics. Now you have to measure this. So did we have any parameter that is going to control how we are going to measure it? Recall what are the parameters that we talked about that influences the signal, right? First thing is, remember that alpha. Oh, I have my signal here, but I cannot measure it. I have to push it to the ground, or the component in the transverse is what I am measuring. So that means the alpha is a parameter that you control, right? So how long you want to apply. So that is your curve. So alpha is one parameter that you can control, depending on which your signal, what you are measuring, might be different. Then Okay, so alpha is under your control. So last class we talked one other thing. So after you push it, you can allow it to dephase, and then I can do an echo, right? So there is a time to echo that we talked about. So that is under our control. Third one is, similar thing. After time to echo, after the excitation is off, then I have to repeat the experiment. So how long do I wait before it all comes back to equilibrium, and then I repeat the experiment. So time to repeat, right? So that is under your control. So last time we talked about the sequence diagram. In there we talked about time to echo as a parameter that you control, time to repeat as a parameter that you control, and of course alpha is a parameter that you control. That essentially depends on how long you apply the excitation pulse. So we have inherent contrast and three parameters that is under our control during acquisition that may control the signal that you are measuring and therefore the contrast. Okay. So pulse sequence parameters, namely your tip angle, echo time, and pulse repetition. Right. So now we are going to use these two concepts and take a simple example case and see how does the difference in black, white, gray, which we perceive as contrast, how does that relate to the tissue type and our pulse sequence parameters? That is what we are going to cover. Of course, in the next module, data acquisition reconstruction, we will go about doing this. Now we are understanding where is the contrast mechanism coming from, how are these parameters controlling the contrast that arises in MR. How we actually execute it will be in the instrumentation and reconstruction. Take an example of a brain tissue, right? MRI, you have seen several brain tissue. So let's take a brain tissue. We have three different types of tissues there: gray matter, white matter, and fluid, the cerebrospinal fluid. You notice these are the properties of proton density T2 and T1, the material property that is inherently different. So this is the inherent contrast that you are expecting from different types of tissue that are there in the brain. So now the objective is, how do I get an image where I can see contrast predominantly due to, because the material is same, it's going to be brain which is going to have three materials. The contrast is going to be mainly due to differences in proton density or differences mainly due to T2 or T1. Notice this material is undergoing PD, T2, T1 is all happening simultaneously. Okay, so now the objective is, how do I get an image that predominantly captures the difference here, or the contrast due to proton density, contrast due to T2, contrast due to T1. Clearly each image is going to look different, right? This is the same slice. This is what we call as PD weighted image, T2 weighted image, and T1 weighted image. This is the same table from last slide. You have different material and different properties. Each of them have different properties. So now you know, or at least you guess, that the white and black in each of this and the gray in between has to be related to, or weighted, more correctly to use the language, it is weighted towards one of the property. So here the black and white and gray are all weighted based on the proton density parameter of the tissue. Here is likewise T2 weighted, here is T1 weighted. Notice qualitatively these images look different, right? So for example, here you see this hourglass shape, right? You see gray, white, black in between, whereas here you actually do not see, you just see the cerebro CSF, right, as a dark patch. That's all you see here. So clearly, and here it is in between. So it depends on what you want to see. The doctors are trained to see, and if this is for normal, if you have abnormal tumor growth, that tissue may have a different T1, T2 PD property, and therefore that may start to show. Okay, this is what is used. So now our objective is to understand what do we mean by PD weighted, how do we get PD weighted, how do we get T2 weighted. Notice it's the same tissue, it has all these three intrinsic properties. Now somehow I have to play with my parameters that is under my control to maximize PD or maximize T2 difference or maximize T1 difference, right? So that is what we are going to see. How are you going to get a PD weighted contrast, T2 weighted contrast, T1 weighted contrast? That is going to be the task. So let's start. Proton density or spin density weighting. This is how do you get this? Let's think about what is the meaning of proton density weighted. So proton density, you're sure where is the signal? When do you get proton density signal? Recall, go back, fundamental, you take the voxel, you wait, put it in the field, you wait for a long time or a short time, right? You don't know the time. You wait for some time, everything gets aligned. So the signal that you get now, the equilibrium signal, the magnetization vector in equilibrium is essentially proportional to your proton density. So that means if I want to get proton density weighting, what do I need to do? I need to wait for a long time. In our parameters, what is a long time? I have echo time, I have a spin time, echo time, I have alpha and I have time to repeat. So let's assume every time I do, I am going to apply enough excitation so that everything is alpha is 90 degree. So that is not a parameter. I always apply alpha so that it is maximum. So then what is the time that you have to wait so that it comes to equilibrium? That means my repeat time has to be very large. How large? I wait until all the different spins are all aligned in the z direction. Therefore, it will be only proportional to proton density. Clear? So if I want density, I need to wait for a long time so that everything becomes in equilibrium. So that is the first idea. So if I want to do spin PD weighted image, I know signal at equilibrium is proportional to PD and therefore I will wait for all the signal to come to equilibrium. How can I do that? I can wait long TR. I will wait for a long time, long repeat time. TR is time to repeat. So when I do that, what happens? If I wait for a long time, even if each of the tissue has different T1 property, I waited enough time that even the weakest guy, the guy that will take the most time to come to equilibrium, I have waited long enough than that guy that now everything has come to saturation. So I don't have the effect of different T1 or the T1 contrast is minimized. Okay, so everything comes back. So now the question is, okay, I have minimized the influence of T1. What is the other influence? T2. So how do I minimize the influence of T2? What is T2? T2 is dephasing. So if I have the signal that is predominantly PD weighted, if I put it to floor, because that's my measurement, only the transverse component is measured. So the moment I put alpha equal to 90 degree, the component comes to floor. If I want to minimize T2 effect, what should I do? That means I shouldn't allow it to dephase. Right? If I don't allow it to dephase, then initially whatever I measure is only based on PD. Of course, then what I can do, repeated measurement. I don't allow it to dephase, immediately I put 180 degree pulse, time to echo, right? I minimize that. So I'm still not having the effect of T2, I have not allowed it to dephase. So that means to minimize the effect of T2, what should I do? The parameter that is under control is TE. I have to minimize TE. I have to have minimal TE. If I have minimal TE, I would not have allowed it to dephase and therefore the effect of T2 will not come into picture. So long TR, short TE allows you to get a signal that is predominantly weighted towards the proton density. Okay. So to put it in picture, these are the two MZ and MXY, the transverse component and the Z component. So if I wait for a long time, what happens? I have different materials. Each one has its own time constant T1 to build up. So I'm waiting for a long time. That way, I don't have to consider the effect of T1. I have allowed each of them to reach their maximum equilibrium value. Now if I push this, so TR is maximum. So now I push this guy to floor. If I push it to floor, this MZ comes to the floor. So the immediate few signal, I'm going to start with the maximum signal. And then it is going to dephase and therefore go down. So now I will do my time to echo as close as possible. before the minimization starts. If I do it long, you see the differences start, T2 differences start to come. So now I push it to the floor and do the time to echo to be as short as possible. Then the contrast that I will get will be, this will be white, this will be grey, this will be whatever. This is my color bar with grey, white to black. So this is the contrast that you are going to get. Clearly you see not much difference between these two guys, which is white and grey, whereas your CSF will be shown nicely. That is what you see here. The CSF is seen, otherwise you don't really see too much of a difference between the other two material. Whatever little difference is there is what you see. Clear? So now you know, by manipulating the parameters, the fundamental signal weightage is given to intrinsic signal of PED. This is what you get from the, how we get it at different locations and all we'll see in the next chapter. But you get a distribution by acquiring it in this sequence. So next is we need to do T2 weighting. This is the T2 image. How do we get T2 weighting? Extending the same logic. If you have a feel for so far what we have covered, it should flow from there. So what is T2 weighting? Oh, T2 has nothing to do with, it has to do with defacing. After you push it to the floor, this is my signal. How it defaces. Time to deface is my signal. Of course, this is T2 star and T2, right? So this defacing is T2. So how do I get that? That means one thing is clear. If I don't allow too much time here, then I will not have T2 effect. That is what we exploited in PD. We minimize the effect of T2. If here I want to maximize the effect of T2. So my T echo, right, should be long enough so that I allow it to deface. The signal should go down. But how do I minimize the effect of T1 and proton density? Right? That is the idea. How do I do that? So here also I don't care about how they start. I am interested only after it falls to the floor, how it is defacing. So that means different material, I don't care about their T1 differences. So that means I will allow it, all of them to go back to equilibrium. Okay. So here long TR I will do. If I do long TR, I will minimize the influence of my T1. Correct? That is what we saw even in the proton density. So minimize the influence of different T1 by waiting for a long time. But instead of short T, here I want long T, so that I can measure T2. So instead of short TE, I am doing long TE. It maximizes the T2 contrast, which is what we want, T2 weighting. So you wait so that the defacing happens. But the problem, as you will notice, is the signal is going weaker and weaker, and I am measuring it as it drops down. That means I am going to have a relatively poor signal to noise ratio. Okay, but this is how you get T2 weighting. So the same thing, wait for a long TR, you maximize, so minimize the effect of T1, then push it to the floor. So this is where the signal, each of them, they start at their saturation or equilibrium value and then start to dephase, and therefore signal is going down. But if I did TE, I would not have captured T2 differences. So now I am waiting for T echo to be large enough such that I get to a region where I can differentiate different tissue based on their T2 differences. Okay, clear? So there is a neat animation here that I would like to show. Right, so we covered T2 here, but the animation here shows long T2 star, short T2 star. Notice the defacing is both due to T2 star and T2. T2 star can be rapid, it's the first part, right? So T2, almost always T2 is measured based on echo. That's what we saw, that one of the sequence, right? We saw how the initial is T2 and T2 star, and then you have T2 differences. So here the same thing. So if it has a long T2 star, then you might get good signal over a longer duration. If it is a short T2 star, the signal will drop down abruptly, so you will have a poor signal to noise ratio. But we are interested in T2. So the T2 signal to noise ratio depends also on the T2 star property at that location. Okay. You can play the animation, rewind it, slow down, and align it to your understanding. Let's stop here. Let's go to the next one is T2. So what do we do for T1? From whatever we covered, this should be straightforward. I want to minimize the effect of T2 here. I want to minimize the effect of PD here. So if you want to minimize the effect of PD, that means what was favoring PD? They allow it to come long TR favored PD. So that means here we want to minimize the effect of PD and maximize the effect of T1 differences in rise time. Then I shouldn't wait for long. If I wait for too long for repeating, everything would have come. The different properties of T1, you won't be able to differentiate. Everything would have come to the maximum. So clearly, if I want to do T1 from whatever we know, common sense dictates that my time to repeat should not be too long. If it is too long, all the T1 properties of each of the tissue, I won't be able to distinguish because everything would become saturated. Okay. So first logic is your time to repeat should not be maximum. So it should be short. The previous two sequences we had long TR. Now we have to do short TR because I want to exploit the difference in T1. So maximizes T1 contrast due to different degrees of saturation. So if TR is too long, everything will become equilibrium. So you won't be able to differentiate one location from another location. So next is, of course, you have to minimize the effect of T2. How do you minimize the effect of T2? Like proton density. Short TE. If I don't have time for echo, then this T2 effect will be minimized. When we wanted T2 effect, we wanted short, long TE. So if I don't want T2 effect, I want short T. Right? It's natural extension from what we covered. Minimizes T2. So advantage here is minimizes T2 means your signal is also going to be good. Okay, so same plots like before. Instead of waiting for saturation, now I am exploiting the difference here in T1. So here I have differences that I want to allow, the rate at which it goes down, right? Goes up in this case, right? That is the T1. This contrast I want. So I'm going to start at a lower level. If I waited here, I got the maximum signal, but I'm stopping in between. So I have some signal. I start from that location and allow it to go down, but I don't allow it to go down too much because then it's T2. So I wait and immediately whatever short TE possible, I'm taking the signal. So now I will be able to differentiate the based on T1, right? Here, white matter, gray matter, CS. Here. So let's summarize, put everything in the context of what we have covered so far. Process involved in MRI. What do you think? First and foremost, take a sample. We started with what? Put it in the static field. Put the patient in the static field, and then you wait until the magnetization reaches equilibrium. Once the equilibrium is reached, you apply another magnetic field, but this time it is going to be rotating magnetic field, right? And what is the rotation frequency? You're going to have Larmor frequency. Once you do this, what happens? You push it to the floor. So your signal comes from M of t precesses around B0 with the Larmor frequency. And then you are talking about longitudinal relaxation and transverse relaxation. And where is your signal coming from? Essentially your transverse component, when it is spinning, you put a coil, magnetic field cuts the coil in a loop, and therefore you are going to get free induction decay. So your signal is coming from there. So finally we do this by exploiting different pulse sequence, and we introduced the sequence diagram, pulse sequence diagram also. Okay. So finally, to summarize, concept wise, we talked about nuclear spin. From nuclear spin, we went on to bulk, when you put many of them in a static field, right? So what is bulk magnetization? The absence of external field. Bulk magnetization, the presence of external field. What did we notice? We talked about the concept of precision, right? And Larmor frequency. So once we did that, what concept did we introduce? Applying another one, pushing it to the floor. Okay. So we talked about alpha pulse and the rotating field, tip angle. Finally, we talked about after you finish excitation, the the two relaxation processes. After the relaxation process, we talked about contrast mechanism. How do we get different contrast exploiting T1, T2 and PD using the time to relax and time to echo. Here, so in the next module, we'll talk about the instrumentation. How do we realize this, right? Instrumentation, and finally about after you get the data, how I'm going to say that this signal is from this location, right? Imaging. How do we do that? Thank you.